SwayamPrabha. Digital India. Educated India.
Hello all. In this video we'll focus on the failures of laminate. This will be continuation to previous videos where we have looked at the mechanics of the laminate. Specifically we discussed about the classical laminate theory, where if the loads are given using classical laminate theory, we should be able to find the strains and the stresses in each of those layers. In this video, we will focus on what are the different failure modes and see how we can use these mechanics to predict those failures. When we discuss about failures, there are two failure modes which are very common, which are the intralaminar failure, meaning that these are failures occurring in a single lamina, and there is another one called the interlaminar failure, where the failure is between two layers. So the first category is about failures occurring within a lamina. So within a lamina, we have already discussed in length about what are the different failure mechanisms as well as the different failure criteria one can apply to predict failure within a lamina. So just to recap, we discussed that fibers can either fracture when we apply tensile load, or fibers can buckle, usually occurs when we apply compressive load to the composite. Regarding the matrix, we said there are micro cracks which can occur in the matrix because of the loading, either tension or compression. And there is also another mechanism where the bonding between the fiber and the matrix is gone, which we call it as the fiber matrix debonding mechanism. These are the common mechanisms in which a composite fails within a single layer of lamina. But in this video, we will also focus on interlaminar failure, and one of the most common failure mechanism is the delamination. Delamination meaning between the two layers there is separation. So probably you recall, what do we mean by lamination? Lamination means it's the process of bringing two layers together and joining them. So delamination is the opposite of it, where we say the two layers or the two lamina debond, and that's what we meant by delamination. So we'll go into the details of both interlaminar failure and the interlaminar failure. So let's start with first ply failure. How do we predict the failure in the first layer? Meaning, like, let's say this is the laminate we see on the screen, and when we apply the loads, it's not like all layers fail in one instant. Usually what happens is, gradually when you apply the load, depending on the load, one of the layers will fail, and after that failure, it's not like the whole laminate is falling apart. No, usually once the first layer fails, the rest of the failures take the load and they continue to sustain the load. So you can apply higher loads even after the first ply. But on this slide, let's focus on how to predict when this first layer fails. For this, we can again use the classical laminate theory that we have discussed. So here I'll be showing you in several steps how to predict this failure. The first step is to say that we are given a stacking sequence. So let's say we have a laminate, and we also know there is a stacking sequence, as well as we also know what are the loads applied, meaning we know these matrices N and M. So the forces and the moments applied to the laminate are known, as well as the stacking sequence and the material properties of these each laminate. From here, how do we go and predict which layer will fail and at what load will it fail? So let's see. Once we know N and M, we should be able to find out the ABD matrices. How do we find the ABD matrices? That's what the classical laminate theory is about, right? So you can find these ABD matrices from Q bar. So we need to know what is the transform stiffness matrix of each layer. Since we know the material properties of each layer, we should be able to know what is Q bar, and from that one should be able to find out the matrices A, B and D. Okay. Next, what do? We use this information to find the mid-plane strains and curvatures in the laminate. How do we find this? For this, again going back to the classical laminate theory, if we combine those two equations, let's say N and M, we combine into one matrix of size 6 elements, 6 by 1, and then I group these ABD matrices in such a way that A, B, B, D. So each of these matrices are 3 by 3, but overall this will be a 6 by 6 matrix times we have these mid-plane curvatures epsilon naught and the mid-plane strains epsilon naught and the curvatures k. So we are already given what are N and M, and we just found out in step 2 what are the ABD matrices. These strains are the unknowns. So how do we find them? We simply need to inverse this equation to find out the strains. So this will be the inverse of this matrix times the N and M. Okay, now that we know the mid-plane strains and the curvatures, how do we move forward? So we can discuss about failure once we know the stresses in each of the layers. How do we find the stresses in each of the layers? We use this information about the mid-plane strain and curvature to first find the strains in each layer. So we determine the strain in each layer. How do we find this? If you recall, earlier we said this can be written as the mid-plane strains plus Z times the curvature. So with this, we should be able to find out what is the strain. When I say strain, this is a summation of epsilon x, epsilon y and gamma xy. So once we find the strains in each layer, then we should be able to find the stresses in each layer. How do we find the stresses? For this, we use the transform stiffness matrix of the kth layer times the strains. So this we do for every layer in the laminate. And once we find the stresses, let's observe these stresses, are they in the body coordinates or are they in the material coordinates? So if we notice, these are actually in the body coordinates xy. So let's transform these stresses in the body coordinates to the stresses in the material coordinates. How do we do that? By simply applying it with the transformation matrix T times the stresses in the body coordinates. Okay, now that we found the stresses in the material coordinates for each and every layer, how can we use this information to find failure? This is when we invoke the failure criteria. You recall, right? Previously we discussed about the maximum stress, maximum strain, Sahil and the Hoffman failure criterions. We can use any one of those or any others from the literature once we know what are the stresses in the material coordinates. So let's say we are applying this failure criteria, and here for example we have used the Sahil. Here let me emphasize what we are interested is to find failure index. But now the question is, what is failure index? So in this equation, the left hand side, which contains this expression sigma 1, sigma 2, tau 1, 2 and the strengths x, y and s, this expression, if you evaluate the left hand side, this should give the LHS or failure index. Okay. Now the idea about failure index is, if it is equal to 1 or more than 1, then that particular layer fails according to this failure criterion. For example, here it is the cycle. But if it is less than 1, then the material is safe. Okay. So from these 7 steps, what are we able to do? We started with a laminate, and we said we know what are the stacking sequence and the loads. From this, we are able to come to the 7th step, where we said for first layer, what is the failure index? Let's say subscript 1 should give the failure index of the first layer. Similarly, for the second layer, failure index 2, and third layer, failure index 3. Let's say we are only looking at a laminate with 3 layers. So looking at these failure index values, can we say which of these is the first failure? It all depends on the values. So the one with having the highest value is the one which is prone to first failure. Meaning, see, it is also possible that for the given loads, maybe all of these laminas fail, or none of these lamina fail, or maybe one of it fails and the other doesn't fail. But how do we know all this information? We just need to put it in a ascending order, these failure index values. Once you put it in an ascending order, the one which has the highest value, that indicates the one which fails the first. Or let's say if your question is only to find which of them fails first, this procedure is good enough. But let's say you want to also know at what load the first ply failure happens, then you need to scale down the loads accordingly until we reach that uh, the layer which is failing, it should reach 1, and the all other laminates, the failure index value should be less than 1. So meaning you need to scale your n and m in a way that the only one of the lamina reaches a failure index of 1 and the rest are less than 1. Okay, I think in summary what we have discussed on this slide is, given the stacking sequence and loads, we should be able to find what is the failure index in each of the layers, and once we'll know those failure index, we should be able to comment on which of those layers fail first, and we should also be able to determine at what load the first ply lamina fails. Okay. Next we move into the progressive failure. Here the idea is what happens after the first ply fails. So here we say that the laminas can bear higher loads even after the single lamina fails, meaning even after the first layer we are mentioning that it can take more loads. So now let's see how that's possible, or how do we can we really predict what is the load at which the second layer fails or the third layer fails. So let's consider this laminate which has 3 layers, and for an example, let's say we are only applying nx. What is nx? These are the forces in the direction x. Okay. Now let's plot what is the relation between the nx value and delta. What is delta? Delta is the deflection along the loading direction. Okay. So since we are looking at a linear elastic analysis, the relation between the force and the displacement will be linear. So, and what is the slope? Slope of this curve is coming from the stiffness of the matrix. So how do we define the stiffness of these matrix? We can define it using ABD matrices. So the ABD matrices define the stiffness of the laminate. So let's say this is the corresponding load at which the first ply fails. So let's say this is something like N1. So meaning the corresponding Nx value at which the first ply fails. After that, what happens is what we are more interested in. So what do you think happens? So if we go back to the previous slide, here after the first ply failure, how do we approach the problem? So what we need to do is, we need to go back to the step 2. In step 2, we need to find the ABD matrices. But now that one of the layer is missing, how do we update these ABD matrices? We simply give, let's say the kth layer is the one which is failed. So we simply say the Q dash of the kth layer is 0. So meaning we are degrading the stiffness of the matrix for the kth layer. The rest all will remain the same. So based on that, you will have a new set of ABD matrices which are updated. This is taking care that the kth layer lamina, which is the first ply to fail, we have degraded to 0. And then we continue with the same process. So once we know the ABD matrices, then we determine the midplane strains, then strains in each layer, then stresses in each layer, first in the body coordinates and then in the material coordinates, and finally coming down to the failure index. What does this do? This helps us to again assess what is the second layer which will fail. The way we are doing is, we are updating our stiffness of the laminate. So as I mentioned, we need to update the A, B and D matrices after failure, and while we update, we ensure that we degrade the failed layer. How do we degrade? We degrade, let's say this is the kth layer, we replace it with a 0 matrix, and using this information we update the ABD. And once we update the ABD, as I showed in the previous slide, the first thing is to find out what are the midplane strains and the curvatures, and from this we find what are the strains in each layer, and from that we find what are the stresses in each layer. And once we know the stresses in the body coordinates, we should be able to find the stresses in the material coordinates 1, 2. And from these stresses in the material coordinates, then we should be able to find out, apply the failure criterion of your choice depending on the material used, and then find out what are the failure index in each layer. So once we find the failure index, that should give us an idea about at what load will the second layer fail. So now the question is, how do we show it here on the plot? So let's say the slope here is the stiffness. After the first failure, will the stiffness remain the same? The answer is no, because one of the layers is absent. Now with that, the stiffness should decrease. So meaning it should have a slope which is smaller than the first slope. And let's say this is the load at which the second layer also fails. So we are saying the slope is reduced, the meaning it has lesser stiffness, because we are only considering a few of the lamina from the original laminate. Okay, so this procedure can be repeated, meaning after the first ply failure, we applied this procedure to find at what load the second ply fails. But even after the second ply, the load is redistributed to the remaining lamina, and then again the stiffness is further reduced. So maybe this is the load at which the third layer fails, or there is complete failure in this laminate. Since we have discussed only 3 layers, we stopped with N3. But let's say if there are 5 layers or 10 layers, one can continue this process until the last layer, and that's when the catastrophic failure occurs. Okay, so with this we have seen how we can really predict this progressive failure by reducing the stiffness of the laminate one step at a time. Okay. So now let's move from intralaminar failures to interlaminar failures. In the last 2 slides, we have discussed about first ply failure and the progressive failure, where we are only focused on the failures occurring within a layer. So that's why we are saying those are intralaminar failures. But now let's see what happens between the layers. So before we look at the failures, first let's look at the stresses between these layers. So first we discussed by saying we'll compare the stresses using the classical laminate theory, and then also with theory of elasticity, where we find the 3D stresses in a laminate. This is important because we know that the theory of elasticity is much more accurate because we made less assumptions and we used rigorous math to come up with the solution. The only reason we focus on the classical laminate theory is because it is much more simpler. The why it is simple, because we have made some assumptions. Now the question is, does all of those assumptions we have made correct or not? We can verify if we know what is the 3D stresses coming from either elasticity theory, or one can also do a finite element analysis for using 3D elements. So we capture the stresses uh, in a 3D fashion. So once this comparison is done, there are some very salient points one has observed. The first thing is focusing on these stresses. What are these? These are the out of plane stresses, sigma z, tau xz, and tau yz. So earlier when we discussed about classical laminate theory, we said each layer is in a plane stress. What does that mean? We are only focusing on stresses in the plane, which are sigma x, sigma y, and tau xy. But the out of plane stresses, which are shown here, sigma z, tau xz, and tau yz, we said we assumed it to be 0. Now the question is to relook at that assumption and see how truthful that assumption is. So once this comparison is made with the 3D stresses, what people found out is this assumption is true, that these out of plane stresses are 0 at the central region of the laminate. Meaning, let's say there is some central region away from the free edges. So these areas we'll call it as the free edge. So we have the same free edge here, and we'll also here and here. So basically these are the free edges of the laminate, and this is the central region. So what we are now saying is, so in the central region these out of plane stresses are 0. So which means in the central region the classical laminate theory truly captures the 3D stresses, but not at the free edges. So at the free edges we are saying that these stresses sigma z, tau xz, and tau yz, they exist. So according to the classical laminate theory, we said that there are no out of plane stresses. But if we look into the 3D stresses, which we come from either theory of elasticity or 3D finite element analysis, we notice that these stresses exist. And why are we discussing about these stresses? Because once we have stresses between two layers, which we now call it as the interlaminar stresses, these stresses beyond a threshold value can create failures at the interface. What do we mean by interface? This is the interface. So interface is the region between two layers, and that's the layer or the interface region. We have said now we see that there are interlaminar stresses, but once these values are beyond a threshold, we said it can fail, and then it will be called as free edge delamination. So why are we discussing about this? Because this is a common way of failure in a composite laminate, and if we don't take any precautions, then this is quite possible in the composite structure. Meaning, while you apply, let's say, the bending load in the laminate, the overall laminate might be strong enough, but the edges, because it has these free edges, then they can open up. Meaning, let's say this is how you expect the intact laminate to be, let's say we are only talking about 2 layers, but because of the free edges, at the edges we might see some failures like this. So this we are calling as the free edge delamination. Okay. So one more important point to note is the stacking sequence does influence the values of these interlaminar stresses, meaning that as a designer of a composite laminate, one should choose the stacking sequence in such a way that one has to minimize these interlaminar stresses. And that is something like design practice one should know. With experience one will know like what is the stacking sequences one has to avoid to prevent these kind of failures. Okay, now let's discuss about delamination. As we said, delamination is the failure mechanism for interlaminar failures. Okay. So in the previous slide, we in length discussed about this delamination occurring at the free edges. But there are other places too we have delamination. I think we already discussed what we meant by delamination, right? Delamination simply means at the interface where two layers join, if that interface is compromised or broken, that's what we mean by delamination. So free edges is just one of those mechanism in which it delaminates. There are other places where it delaminates, such as close to holes. Let's say in a laminate, there is a hole which is drilled at the center. So while the drilling this hole, there is a good chance that one can create these delaminations if the drilling is not done properly. Meaning, because of this, once you drill a hole, again you create it as a free edge, because now it's again exposed to the outer, because the surface of the hole is exposed, now it is acting as a free edge, and that is why close to the hole there is a good chance that again it has these free edge delaminations. And it can also happen at ply drops and joints, meaning, let's say, how do we join two composite structures? Let's say this is one structure and the other structure is here. We join this using a material called as adhesive. So what we are showing here is a composite adhesive joint. Meaning, like, we have used a adhesive to join one layer of the composite to the other layer of the composite, and here we are saying because of the loads the failure can occur here. So let's say we have a failure here, then basically we have a delamination occurring at the joint level. But there is another instance of delamination. Let's talk about the low velocity impacts. So usually low velocity meaning we are not talking about very high velocities, but let's say like a tool drop. Let's say we are talking about aerospace structures, and let's say there is a wrench one workman is holding and he dropped it on a composite panel. What happens? On the surface you won't see any damage, because let's say there is no dents which are occurring on the surface. But below the surface of the laminate, maybe, let's say this is the cross section of the laminate we are discussing, and let's say it has 3 layers. Okay, so layer 1, layer 2, layer 3, and we are talking about this drop. So one, because of this dropping an object on this laminate, it can have a dent on the surface. But in addition to that, now what we are saying is it could create some delamination between the layers. This delamination is very common in the composite industry, and it is very dangerous because one cannot see this failure with a naked eye. because this is beneath the surface, you cannot have access to that. So on the surface it looks fine, but within the surface there is a delamination. But what is the problem with a delamination like this? Because it reduces the stiffness of the laminate. So I think we recall initially we discussed where does the why does the stiffness of the laminate is high? Because these are all bonded with each other. Once that bond is compromised, then the stiffness of the laminate also is compromised, which may not be good, because we have designed this structure assuming that it is stiff. But now that the structure is less stiff, the structure can be unsafe even though there is no fracture, meaning this delamination can do two things. One, it can stay there and not grow. If it grows, it will grow into a complete big fracture and it will break it into two pieces, which is catastrophic, which is of course one has to avoid. But even though there is a delamination and let's say it's not growing, it's not like we should be okay with it, because it reduces the stiffness of the structure and could lead to failure. So in summary, on this slide we have seen what are the different ways delaminations can occur in composite structures, and we also emphasize that because of this delamination it can either lead to catastrophic failure where the crack propagates to the entire length of the laminate, or even if there is a delamination which doesn't go, it reduces the stiffness, so it might affect the performance of the structure. Lastly, we will also talk about free edge delamination and see what are the ways one can avoid these delaminations. So there are two strategies. One, either you do a edge reinforcement or do an edge modification. So in the edge reinforcement, we are discussing about an edge cap, meaning at the cap you put a reinforcement which, like a staple, it holds the all the layers together, uh, basically to prevent the free edge delamination. Or the other way is you basically stitch all these layers using a rope or something. And thirdly, one can use an extra layer of adhesive so that the bonding between these two layers is strong, and then you need very high stresses to delaminate these layers. And for the edge modifications, one can reduce these interlaminar stresses by multiple ways. One, either by ply termination, meaning let's say this is a 5-ply laminate, but towards the edge you only have 4 plies. This is one strategy of decreasing those interlaminar stresses. And two, we can introduce this notch. Why do we introduce notches? Because that reduce the stresses in the peripheral region. So around the notch, the stresses are, let's say the stress concentrations are reduced, which means the effective stresses are less. Since the effective stresses are less, it is less prone to fracture. And tapering is also in a way related to this ply termination, but the only difference here is we are gradually decreasing the thickness. So let's say this is the zone where we gradually decrease the thickness of the plate. So let's summarize what we have discussed in this video. We first started by differentiating what are intralaminar failures and interlaminar failures. Intralaminar failures, we said, are the failures occurring within the lamina. So in that aspect, we discussed how can we find what is the first ply failure, meaning the ply which will fail first. How to identify that we have seen with a 7-step procedure. And later we also discussed about progressive failure, meaning if we continue to load even after the first ply fails, will it take the load? We have discussed and shown that it does take higher loads, but then it takes higher loads until the second ply fails, and consequently it keeps on taking the loads until majority of the plies fail. And lastly, we also discussed about this interlaminar failure, where we discussed it is mostly because of the stresses. So we said these interlaminar stresses usually build up at the free edges. So these interlaminar stresses, when they build up at the free edge, they are prone to failure. When these stresses are beyond a threshold values, they open up or delaminate, which we are now calling it as the free edge delamination. And we also looked at the other ways in which delamination occurs. So these delamination can also occur at the holes, or maybe because of small low velocity impacts like drop of a tool, where we said there is a damage not occurring on the surface of the laminate but within the laminate. So there is a delamination occurring within the laminate which is not visible to the naked eye, but it is dangerous once we have this delamination, because either it could lead to a catastrophic failure, or it can also decrease the stiffness of the laminate, which in turn will uh, affect the performance of this composite structure. With this, we conclude our discussion about the failure of the laminates. In the next videos, we'll be looking at few design principles we need to follow such that we design or we come up with a very reliable or a durable laminate. And we'll also discuss about composite sandwich structures which are commonly used in automotive and aerospace industry because of their lightweight advantages. See you then. Bye.